There are these incredible invisible forces at work all around us every single day. They're strong enough to hold back a literal mountain of water, but they're also subtle enough to make a skyscraper dance in the wind. Today, we're going to pull back the curtain on the science that governs just about everything. Let's dive right in. Okay, just look at this thing. A giant concrete dam. It's an absolute monument to human engineering, right? But what is it really holding back? It's not just water. It's the immense, silent, crushing pressure of a fluid that's perfectly still. Now, let's switch gears. Let's swap out that water for air. You see, a skyscraper isn't just sitting there. Nope. It's in a constant battle with the wind. And we're not talking about a gentle breeze here. This is a powerful fluid in motion, pushing and pulling on every single square inch of that building. Or how about a bridge pier standing right in the middle of a flowing river? It's in a perpetual tug of war with that moving water, a fluid that is relentlessly trying to push it over second by second. All right, now let's bring it all the way home. When you turn on your faucet, you're seeing the very end of an incredible journey. That water traveled through this huge, complex maze of pipes. It was pushed along by powerful pumps, and the whole thing works because it all follows the same fundamental set of rules. So, a dam, a skyscraper, a bridge, and your kitchen sink. They seem totally unrelated, don't they? But they are all connected by one single powerful science. So what is this invisible force that ties them all together? Well, the answer to our little mystery, the culprit if you will, is a single simple concept, the fluid. That's it. It's the common thread, the unseen star of the show in all of our examples. And that leads us to this amazing field called fluid mechanics. It's the science that basically gives us the rule book for how fluids behave, whether they're sitting still, like the water behind that dam, or moving, like the wind whipping around a high-rise. So what in the world is a fluid? Well, scientifically speaking, it's any substance that just keeps deforming or changing shape when you apply what's called a shear stress, no matter how tiny that stress is. A simpler way to think about it? Imagine running your hand across the surface of water. It just flows and gets out of the way, right? That's it. That's continuous deformation in action. And the difference becomes crystal clear when you put a solid and a fluid side by side. Think about a solid, like a brick. It holds its shape because its molecules are packed in there super tight and they can resist those shear forces. But a fluid, it just takes the shape of whatever container you put it in because its molecules are more spread out and they just can't fight back against that force. They have no choice but to flow. But wait, there's a little twist here. The word fluid isn't just for one thing. It actually covers both liquids and gases. And yeah, while they both flow, they do it in some very, very different ways. And here you can see the key differences. Liquids, they're really hard to compress, and they have a fixed volume. A liter of water is always a liter of water. It doesn't matter what you pour it into. Gases, though, are a whole different story. They're super easy to compress, and they'll just expand to fill up any space you give them. It all boils down to how much the molecules are attracted to each other. It's way stronger in liquids, which is why you get that distinct free surface on a glass of water, but not in a room full of air. Okay, so if these things are always moving and changing shape, how do we actually study and predict what they're going to do? Well, scientists and engineers have a kind of toolkit with different branches of study, and each one builds on the last. First up, we start with fluid statics. Statics just means at rest, so this is all about the pressure in a dam or a tank. Simple enough. Next, we have fluid kinematics, which is where we study the motion of fluids, the how they move, without getting bogged down by the forces causing it. And then the big one, fluid dynamics. This is where we bring it all together, studying fluids in motion and all the pressure forces that make them move. This is how we can analyze everything from the lift on an airplane wing to the flow of blood in our veins. So now that we have these tools in our belt, we can finally go back and solve that initial mystery. We can see exactly how fluid mechanics is the invisible architect of our entire world. Seriously, every single time we manage water, we are using fluid mechanics. Designing dams to handle all that pressure? That's fluid statics. Building irrigation systems to get water exactly where it needs to go? That's all fluid dynamics. And those incredible pumps and turbines that generate our electricity, they are absolute triumphs of fluid engineering. And it's definitely not just about water. Understanding how air flows around a skyscraper is what keeps it from swaying dangerously in the wind. Predicting the force of a river on a bridge pier is what keeps that bridge from collapsing. Heck, even analyzing how water flows underground is critical for making sure buildings have stable foundations. It is all fluid mechanics. So once you start looking for it, you realize you're constantly surrounded by and interacting with fluids. Understanding the principles that govern them is really understanding a fundamental part of the world you live in. And it all comes back to this one really elegant definition. This is the heart of everything we've talked about. From the air you're breathing right now to the water you drink, if it flows, it's a fluid. And that means we can understand it and we can predict what it's going to do. So, next time you see steam rising from a cup of coffee, or you watch leaves dance in the wind, or you even just turn on the tap, take a second and remember the beautiful hidden science of flow that's at work. Now that you can see this unseen force, what flow are you going to notice first?